Now that we've covered standardization, I'd like to talk about one of the most beautiful and useful continuous distributions in nature and in data mining, and that's the Gaussian or normal distribution. It looks something like this. It has a number of very interesting properties. The shape is Gaussian. What makes it standard is that we set its area equal to 1, so it is useful as a probability distribution function. We set its mean, what do you think, for standardization? Equal to 0. That's right. And we set its standard deviation, which of course also means its variance, equal to 1. And we now have our standard normal distribution. So let's talk a little bit about the properties of this very nice shape. At the top, it's just a little bit under 0.4. It's about 0.399. And what it is exactly is 1 over the square root of 2 pi, which is kind of cool if you're a math nerd like me. A couple interesting things about this shape. It's generated by a function that has a normalizing constant. Okay. That gives us the value of each point on this curve. And when we have a Gaussian distribution that does not have mean 0 and does not or does not have variance 1, then we need to modify this formula. But this is our basic formula, but you don't need to know this. You don't need to calculate this. You can just calculate this in Excel or on your calculator. But here are some interesting properties. The full integral looks like this. So what that means is that it goes all the way from minus infinity to infinity. The area under the curve is what we call our cumulative probability distribution between something and something else. So if we want to know how much probability is to the left of a particular z-score, say, that's very easy to calculate. We get rid of this infinity and we substitute in our z-score. Okay? And that will tell us that area will be our cumulative probability to the left of our value z. So we have 0 in the middle, we would have z, and our cumulative probability is everything to the left, like so. Okay? So there's a couple very interesting things about this curve. On the one hand, it goes from minus infinity to infinity, which sounds like a long ways. On the other hand, most of the probability is concentrated right around 0. Let me show you what I mean. If we go out to z equals 1, we're already at 0.841. So we have 84% of probability is to the left of 1 standard distribution. If we go out to z equals 2, and just to be clear, we're changing this value right here. So we're saying how much is the area from minus infinity to 2. This would be 0.977. If we go out to 3, we'd already be at 0.998. And if we went all the way out to z equals 4, we would be at 0.999968. Now Excel makes it quite easy to calculate with two very convenient functions. One is called norm S inverse. Okay. So we have norm S dist and norm S inverse. One is for calculating the probability from a z-score, and the other is for calculating a z-score from a probability. Norm S dist takes as its input a z-score, and it outputs the cumulative probability. So we would put in z equals 2, and we would get out 0.9772. Okay. Norm S inverse inputs a probability. So you'll notice that this value always needs to be between 0 and 1 inclusive, and it outputs a z-score. Almost all the problems involving probability throughout this entire course can be done using these Excel functions when we have normal distributions. So when you hear people talk about a parametric model, they mean a model where the probability distributions of the input data, the output data, and the noise are assumed to be regular. And if they don't specify, they generally mean that they are Gaussian.